No, I don't think
Yo, I think it's like one half.
Needed its simplest form.
How do I not know this?
0 plus 1.
Oh, just get together.
Just doing like X minus I.
You should think about it. Try harder. Let's talk to each other. Wake up.
Or it's imaginary.
There's a coordinate. Try things.
A says that 1 minus e to the 4th equals 0. Okay, do it. You want to
If I do that against your binder. Yep. Yo.
I like that.
I'm not trying to be adopted.
What time were you looking at?
Take some
Because I don't know what that even is. That's just not a complex. I don't recognize that as a complex.
literally musical.
Wait, I'm so loud.
Complex number is a number of the form a plus b where a it's a fundamental paper algebra, but it's true, and it is. That this polynomial has 4 complex terms.
Look into it.
You're asked to find those 4 complex terms.
Yo, that
Square
makes
divide is not a real number.
Okay.
Well, honestly, if you try hard,
Hey Matthew, if you want to get good.
What is 4 9?
Alright, I got it.
You know how this is something you know how to do. Usually most years figure it out after like a few minutes.
So you have two.
X squared minus I, x squared plus I, because you would want to do like the root of that. But root I is not a thing. Or it isn't. Would you like a tiny hint?
No.
Right. This is a pretty tiny hint. Basically, we just need to solve the equation x to the 4th plus 1 equals 0. Which you did last year. You did problems like this last year.
wait, can you write it as like 0 plus 1i half?
No, that's not a thing.
Darn it.
Yeah, a real number, a complex number is a number of the form a plus bi, where a and b are real. Wait, so the collective power of the sophomore class magnet program should be able to figure out what to do. How do you solve this equation?
Wait, so I guess the 5th is not. I should figure this out.
Square root of that is I. No, that's not it.
No, I've done this before.
A plus b.
Period H is at home.
Waste the time.
Yeah, you do. Okay, here comes hint number 2. You're trying to solve the equation x to the 4th equals -1.
Yay.
You did this last year.
Oh! It's just the quadratic formula after that. Okay.
Even if we square root of I.
Oh, so close. I had it and I was like, what the hell am I supposed to do?
How is it question?
You just get square root of I.
Oh, you could, right?
All right. On behalf of math teachers everywhere, I'm sad.
Hi, Seth.
No one knows what to do?
No, wait.
You express this in the polar form of a complex number.
Wait, cosine theta plus
Yeah.
cosine theta?
What is negative 1? Negative 1. Negative 1 can be represented on the complex plane as like that point,
I
right?
don't think we learned that though.
Which is what?
Like, I don't think we did Euler's formula.
No, we did.
Not Euler's formula.
Cosine.
So wait, hold on. There's this whole thing you guys did last year, right?
Yeah,
We were like, yo, every complex number, so take a number on the complex plane. This is the real axis, this is the imaginary axis, and suppose the number is represented as a plus bi, right? Alternatively, you can represent that same number with how its distance from the origin and its angle, right? And what you guys did last year with Giles is you said, okay, well that is, then the real, if that's r and that's theta, then the real component is r cosine theta, because duh, and the imaginary component is r sine theta. Is this coming back to you guys at all?
Yeah.
Okay, so this same number, a plus bi, can be represented as a complex number with real component r cosine theta and imaginary component r sine theta. And usually what people do is they factor the r out and they write it as r times cosine theta plus I sine theta, and that is a complex number, and people will even abbreviate it r cis theta.
Oh.
Okay, so another example, since you guys are feeling pretty weak on this, you can do like some sort of, so take the complex number like, let's see, negative 2 root 3 plus 2. Yeah, 2i. Well, I can plot that on the complex plane. And on the complex plane, that looks like I go over negative 2 root 3 and then up over here, right? So that's just that number. Well, that same number can be represented with its angle and its distance. How far is that point from the origin? Too slow. 4, thank you. Yeah, good. Over negative 2 root 3 up 2 is just 36 90 triangles. So that's 4, and what is this angle? 5 pi over 6. Class, get it together. That should be really much faster than that. Yeah, good. So therefore, this same number, negative 2 root 3 plus 2i, can be written in a different form. The form being 4 times cosine 5 pi over 6 plus I times sine 5 pi over 6.
It's 4 cis.
And this, by the way, if you just multiply this out, like what is cosine of 5 pi over 6? It's negative root 3 over 2, right? So negative root 3 over 2 times 4 is negative 2 root 3. And what's the sine of 5 pi over 6? 1/2, so times 4 is 2i. So I'm not like doing anything crazy here, right? This is just a different way. These two are just two different ways of writing the same thing. Right? Is this coming back? Okay, good. So why is this so useful? It's so useful because if you give me a complex number like r1 cis theta 1, and you multiply it by r2 cis theta 2, then really nice things happen. The answer is r1 r2 cis theta 1 plus theta 2. Did this whole unit just get like deleted from your memory, just like 100%? It's really sad.
We did
Definitely did
Like
this.
one class on it.
We did like
Yeah.
full.
No,
we did some serious stuff on this. It just wasn't as.
It wasn't on the test.
We
so
tested
it wasn't-
All right, good. This is why freshmen shouldn't be in Precalc. All right, good. All we're gonna do this is like a fact. You can prove this. It takes like 1 minute. And it's also true is that if you take a complex number like r cis theta and you raise it to the nth power. You did do this, yeah. Then this is just like r cis theta times r cis theta times r cis theta times r cis theta. Like a bunch of them, right?
Alright.
and r cis theta. So what does that turn out to be? Well, based on the above rule, you're going to have r to the n cis theta n. And this is called de Moivre's theorem.
Can you spell that?
Or however, can't pronounce French properly. Okay, good. So, what do we actually do to solve this problem? I'm doing this for you now because you guys don't remember anything. -1, you represent the number -1 in polar form. What is -1 in polar form? It's like 1, the radius is 1, and the angle is 180 or pi. So this is just like cis pi. And then, this is how I do it at least, is I say, okay, let me write this in a couple different ways, right? So I'm going to say x to the 4th is cis pi, but I could also go around the whole circle again, and I could write it as cis 3 pi, and I could go around the whole circle again and write it as cis 5 pi, or cis 7 pi. These are all the same, because pi, 3 pi, 5 pi, and 7 pi are all coterminal. And then you raise both sides of this to the 1/4 power. And you get that x is cis pi to the 1/4 power, cis 3 pi to the 1/4 power, cis 5 pi to the 1/4 power, and cis 7 pi to the 1/4 power. And what happens?
Yeah, so it's just cis pi over 4, cis 3 pi over 4.
Yep. Yeah, it's like 1 to the 1/4, and then it's cis pi over 4, and then this is cis like 3 pi over 4. Is this starting to come back?
No.
5 pi over 4, cis 7 pi over 4. And what is cis pi over 4, by the way? Yeah, just do it with the geometry. Just picture pi over 4 and then just like give the answer.
Root 2 over 2 plus
Root
I
2 over
sine
2
2
plus
2.
I root 2 over 2.
I sine.
Or I guess you could do it like this. Cis 3 pi over 4 is?
One of them is negative.
Negative root 2 over 2.
Negative root 2 over 2, of course, because of quadrant 2, right? Plus root 2 over 2i. 5 pi over 4 is negative root 2 over 2 minus root 2 over 2i. And cis 7 pi over 4 is root 2 over 2 minus root 2 over 2i. Ta-da! We win, right? These are the 4 complex roots of f of x equals x to the 4th. And so, again, the fundamental theorem of algebra wins. All right. That was supposed to take less time. All right, I'll give like some homework on this, like 1 or 2 problems to just get you back in the game. But if you're talking about the complex roots of polynomials, we should get back to problems like this where we know how to do it. All right, good. Let's do another activity. I have a worksheet for you, or I have this is copied from that same textbook, that Forster textbook. Usually I give this for homework, but I sort of forgot to, so we're just going to do it in class. I think the whole thing only takes like 5 minutes. So that's... So, I'm giving you this thing. It talks about the fundamental theorem of algebra, it talks about the remainder theorem, the rational root theorem, etc. And then on the back there's like these numbers 1 through 20. And 1 through 20 asks you to make 20 graphs.
Oh. Wait.
So, yeah. So take a piece of paper and split it up into 20ths and draw a picture of a graph meaning each of these things.
So, front and back.
Just like do whatever you want, it doesn't matter. It's like make 20 graphs, go.
10 on each side.
Do we have to put it in, or can we like keep it in our notes?
Yeah, you can put it in your notes. Yeah, boom.
Expensive and
Good.
you're not
It doesn't have to all be on one.
Can I erase this stuff?
Yes.
Just draw like a bunch of pluses.
Yeah, just like that. Just like chill. What's up? Yeah. So I can take pictures of that. You print them later, or you just look at them?
never mind.
Both a zero? What's multiplicity of 2?
Oh yeah,
Reading the
multiplicity
paper?
of 2 is like Fortune's weird old-fashioned way of saying double root.
Wait, what?
It doesn't matter.
No, like
The way to train functions work is
you go around. Yeah, the directions are sketch a graph of the polynomial function described. Some of the graphs may be impossible.
Keep a function of no real zeros.
And then he also says the word complex will be used to mean non-real complex number. That pisses me off because why don't you just say non-real then, Forster?
4 or 5 are impossible, right? Yeah, 4 or 5 are impossible.
Wait, that's how
Yes, these are just nice steps. Wait, she can also
Zero. Does that mean what is number 2?
Oh, no,
It's gonna take
Is
longer
6
than I thought.
impossible?
I think it's
6
gonna take
impossible?
longer than I thought.
Let me think
Yes.
about 6.
Can I just assign this for homework and we'll go over it later?
No.
Yes, please.
That's more homework.
It's the only home.
Is 6 impossible?
No, don't do it. Don't do
I think you
it.
guys can do this whole thing in 5 minutes.
You can't even fold paper that quickly.
Wait, I think we should do this. I think we should just do this. We'll just go over it. It's not that much fun this one, just do it.
6? You need 2 negative zeros.
This doesn't work, right? Because you have to have a positive y-intercept too.
Does 4 work?
4 doesn't work.
Okay, that's the following.
All right, class. Good. I tricked you. We're gonna just do this. Or you're gonna just do this for homework because it's not hard. It takes like 10 minutes, but it's not our best use of class time. So we'll go over this next class on when do I see you guys? Monday or something?
Yeah.
Okay, good. All right. So new activity. This is what we're actually gonna do now. Take out a whole other piece of paper.
Wait, graphing or no?
Yeah, if everyone was as fast as you, we could have just finished, but they're on like number 3. All right, so label this piece of paper like this was like Mr. Rose's takeout. So get a new piece of paper and go landscape on this piece of paper. And this is actually kind of a cool thing. I invented this lesson, and one day I will be famous for it. You're proud of me?
Wait, what are you gonna call it?
Give it no title yet. We are going to be just discovering things. So the title will come later. Alright, what we are going to do is we are going to consider every conceivable polynomial. I should say what the overall goal is. The goal of this investigation, which we are beginning, is to predict the number of positive real roots a function has based on the signs of the coefficients. Predict the number of positive real roots that a polynomial, I guess I should say, has. Predict the number of positive real roots a polynomial has based on the signs of the coefficients. Okay, so if the signs of the coefficients are what's relative, then we're gonna just like consider every possible combination. So okay, let's do it. What's the simplest polynomial that we can think of, a 0-degree polynomial. And we're going to make a big polynomial tree. So we have, like up here we'll have like f of x equals 2. And then like way over here, I told you guys to go landscape, right?
Yep.
F of x equals negative 2. Alright. And we can, now we're going to make little graphs of f of x equals 2 and f of x equals negative 2.
Nice.
Alright. Now, of course, I know what these two polynomials look like. This one just looks like this, and this one just looks like this. Okay, so in both cases, how many positive real roots are there? None. So done. Alright, now what I want to do is I want to add a coefficient. So let's add the coefficient 5x to each of them, or negative 5x. And so I'm going to consider now 4 functions. I'm going to consider the function f of x equals 5x plus 2, f of x equals negative 5x plus 2, and then f of x equals 5x minus 2, and f of x equals negative 5x minus 2. Because remember, the overall goal was try to learn, based on the signs of the coefficients, how many positive real roots there are. And so we have to consider all possible like combinations of signs, right? Okay, so I'm going to make 4 little graphs. And so like, here's the thing. I'm going to be slightly obnoxious now, which is I don't actually care about the left-hand side of the graph at all, because I am only looking for the number of positive real roots. So only the right-hand side of the graph interests me. All right, so let's talk it out. Each one of these functions is kind of a story. F of x equals 5x plus 2. We begin the story when x equals 0. Where am I when x equals 0? 2. All right. And now, what effect does this 5x have on this function as x gets bigger? It just makes it go more up high in the sky. Cool?
It's not linear.
Yeah, it should be linear, but I don't care about that. I'm being silly, because only whether it's going up or down matters. Okay, so how many real roots do I end up with here?
0.
0. Okay, so we're going to log that next to each one of these. We're going to say the number of positive roots. Okay. Whereas, on the other hand, consider the function negative 5x plus 2. Where do we begin our story?
2.
At 2. And now, what effect does this negative 5x term have?
Down.
It makes it go down. And are you guys feeling this? Like, no matter what, it's going to go down. We are just going to have a root. Because even if this number 2 were not 2, but instead was 2 million, give me some vigorous head nods. And even if this linear coefficient were like 0.05 or something, no matter what, eventually this negative linear term would overpower this constant term. So every term has its like moment to shine where it is the most powerful. When x is 0, the constant term is the most powerful. But when x is big enough, this term will overpower this one, and we are therefore guaranteed to have one real root. Cool? Say cool.
Cool.
Okay, going a little faster. How about now? Where do we begin? The story.
-2.
At -2. And what effect does the 5x have?
Terrible
It
job.
makes it go up.
Absolutely terrible.
And so no matter what, I am going to have exactly one positive real root. How about over here?
It goes a -2 and it goes down.
Yeah, now we start at -2, and the negative 5x term is merely going to make me go down even more. So I'm guaranteed to have 0 positive real roots. Okay, we're going to add one more row to this chart. And let's add like 3 or something. So this takes a minute, so I'll give everyone a minute to like sort of draw. So I'm going to consider 3x squared plus 5x plus 2. Has everyone got the pattern kind of under control? And negative 3x plus 5x plus 2. So in the next row of the tree, consider adding a positive coefficient quadratic term and what's up? Square. Consider adding a positive and negative coefficient quadratic term to the front of each of the previous graphs.
Landscape, my dude.
Stop complaining about space. Just suffer silently.
Mushies.
Damn.
I'm sorry.
You got a whole other board.
Okay. I think what we should do is put it here and just take a wide view of things. Yeah. Because it's hard to get it all in, so we'll just take a wide view. Okay.
Yes, sure.
Leave a little space underneath.
What?
If you didn't leave enough space, suffer silently. This is my new catchphrase. This is pretty great.
No, it's not.
Yeah.
That sounds like something that they say during like a revolution.
Wait, who is revolutionary or the dictatorship?
Dictatorship right before a revolution. Silently.
I mean, it could also be like an ironic, like, revolutionary.
All right. Are we all good? Okay, good.
Good.
Okay, good. Let's begin. Let's begin. Let's go to the cards. Woo. All right, Margaret, you're up. 3x squared plus 5x plus 2. Tell it as a story. Say once upon a time x was 0. Louder. When x was 0, what was the value? 2. Okay. And then, this is where it gets interesting. What's the sort of next thing that happens? When x is very small, which of these terms is like more powerful? This is a little bit subtle.
No, it's 5x.
Well, it's a little bit hard, that's a little bit of a vague question, but there is a fact which is, between, everyone, this is an important point, between 0 and 1, which is bigger, x or x squared? X is bigger, right? So the 2 is important when x is 0, but then as x starts getting bigger, the 5x term will dominate the 2. And then, eventually, as x gets like big, the 3x squared term will dominate. So you didn't really tell the story properly, but this real story is once upon a time x was 0, and the value of the function was 2, and then the 5x term contributed how? Positively or negatively? Positively, and then the 3x squared term contributed even more positively. So, okay, how many real roots? Positive real roots. 0. Good, next one. So yeah.
Okay, so once upon a time, when
Stop
x
taking everything
was
as
0, it was actually 2.
Yeah.
And then from 0 to 1, 5x contributes, so it went like up. But then like it got bigger, and then like its future started crashing down on it.
Yeah, exactly. Yeah, it's a rags to riches to rags story or something like that, right?
Yeah.
Or no, it's just riches to rags.
Yeah.
Because we started 2, and then she said the 5x term will start to dominate. The 5x term is going to contribute positively towards this polynomial. So up, right? But then eventually the negative 3x squared term, no matter what, the x squared term will dominate eventually, because when you square big numbers, they're so much bigger. So does everyone feel it? Even though this might go up for a while, this is guaranteed to send me down again. And so, no matter what, it might not look exactly like this, but no matter what, I can conclude that there will definitely be one positive real root. Follow? Okay, good, next. Anthony.
Once upon a time there was, when f of x was 0, it was 2. And then the negative 5x would make it go down. What when it's 0 to...
Yeah, this will start to, the negative 5x term will start to contribute negatively towards the function. And so we're going to go down, 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 cross the x-axis, and then what?
You go even more down.
More down?
Or...
And then? What is the 3x?
Okay. Oh yeah, it goes up.
Yeah, then the 3x squared term eventually will overpower this negative 5x term. And so we're going to cross back up. So how many real roots?
How do we know that it'll go below the x-axis?
Yeah, Nate's not buying this crap story that I just gave you guys. Remember I told you to be skeptical all the time? How do we know it's going to do that? Do we know it's going to do that? No, we definitely don't know it's going to do that. It might go down a little bit, but then who's to say it's going to cross the x-axis before the 3x squared term takes over?
Yeah, solving for 0.
Yeah, but like the answer is, can we conclude that it's going to have two roots?
No.
No. Might it have two roots?
Yes.
Yeah, 2 or 0. Yeah, so this picture, this graph gets two pictures. That could happen, or in a slightly different version of the story, the 5x term might bring us down a little bit, but the 3x squared term will take over before hitting the x-axis. So it is also possible in this situation to have no real roots.
You can also give like
Cool.
a little...
You could also have one, if it touches exactly, we're going to count that as double, as 2. All right, good, let's go a little bit faster now, because I think the big picture already happened. How about this one? Let's tell the story. We start at positive 2. What effect is the negative 5x term going to have?
Down.
Down. What effect is the negative 3x squared term going to have?
Down.
Even more down. Boom. Guaranteed one positive real root. Good. Next. Now we start at negative 2. What effect is the 5x term going to have? Up. What effect does the 3x squared going to term have? Up even more. Guaranteed, therefore, to be one positive real root. Cool? Okay. How about now?
Catch me up.
This is the one where you
This is the tricky one, says Neil again, right? Because one thing that could happen is we could start at negative 2. The 5x term could overpower the negative 2, take me above the x-axis, before eventually the negative 3x squared term overpowers and we crash down, giving me two real roots. That's possible, but it's not guaranteed. What's also possible is to start at negative 2 and the 5x term brings me up, but the negative 3x squared term takes me back down.